Hi there, I'm Stephan Lavavej, Visual C++ Libraries developer, and welcome back to Core C++ Part 5, in which I'll be covering explicit and partial specializations of class and function templates, although only 3 of those 4 things are possible. So in the previous parts of this series, we'd gone through essentially what happens when you call a function in C++, and we had covered template argument deduction, which is what happens when you call a function template. And I'd shown a bunch of function templates, but there's actually another way you can customize what happens with function templates, and that's specializations, and this applies to classes as well. First I'm going to start with classes because they're a little bit simpler for what I'm trying to show. Here I've got template type name t struct kitty. As I promised, it's all cat noises all the time. And it just has a static member function meow. I don't really even care about the content of this static member. I just want to show what happens when I try to use the class. And then I've got a main function here that calls this static member function meow with 3 different kinds of kitties. Kitty for int, for const_char star, and double. So because I only have this one template, this is called a primary template by the standard, what will happen is that kitty tmeow will be printed 3 times. So this shouldn't surprise anybody. And that's exactly what we get. Now, suppose that whoever is the author of this class template, of course, kitty is completely useless. Imagine it's like vector, or perhaps I'm writing my own class, and I care about a certain kind of type. I want to do something special, say for const_char star. It's like, oh, this class needs to know something special about strings. Well, I can define what's called an explicit specialization of a class template. A bit about terminology. If you look at the standard, explicit specialization is the actual name it uses. It says an explicit specialization of any of the following. And the problem is that explicit specialization is perhaps not the clearest term it could have used. You'll see some book authors and just people writing will sometimes refer to these as full specializations to contrast them with partial specializations. And that terminology is actually fine. That doesn't introduce any confusion. It's just that the standard likes to say explicit specialization, even though it might be a little unclear. So that's the term I'll use for now. So imagine that I want to do something special for const_char star alone. I can write an explicit specialization of class template by saying template empty angle brackets struct kitty, like this. And then I can put whatever I want inside, like static void meow. I can collapse this as well. And here I can say, oh, I'm doing something special. So I could put any arbitrary code in here, but I'm just going to print out something. Oh, and I need to say what this is specialized for. And I want this one to be for const_char star only. And this will print kitty const_char star. And close it off. Still getting used to typing on this new laptop's keyboard. And if I compile and run this, I would expect the primary template, this completely generic one for T, to be used for int and double star. And this explicit specialization to be used for the const_char star. And if I compile and run, that's exactly what I get. So I was able to essentially replace the primary template for a specific argument that I wanted. So this can work for any number of arguments. Imagine that I had a foo class templated with template type name, whatever, on like A, B, and C. I could write an explicit, so this would be the primary template. I could write an explicit specialization beginning with those empty angle brackets for something like foo of int, long, and like int star. So this explicit specialization would be selected only when A is int, B is long, and C is int star. And as we had seen in earlier parts, the matching that the template machinery does is exact. It's not going to permit like const qualifiers to vary. So in this case, because I've explicitly specialized kitty for const_char star, this will not be selected for just modifiable char star. That's a different type as far as template machinery is concerned. But there is a way to say, okay, I'm specializing kitty not just for one particular type, but for a restricted set of types that's less than the full universe of t's. And this is called a partial specialization of a class template. So the way that this looks like is I would say template, and I'm just going to get more and more complicated as we go here. Imagine template type name, here I'm going to say x, struct kitty for arbitrary x star, and then in here I can say x star, like this. So now I'm saying, okay, I've got a primary template kitty for arbitrary t, but if that t matches the pattern x star, whatever x is, then I'd like to use this other one. So here I would expect the primary template to be selected for int and x star to be selected for const char star and double. And indeed, if I compile and execute, that's exactly what I get. So this is a partial specialization. It's saying this one is for, like I said, a restricted universe of types. And this is often where people start to get confused. So here I'm just going to scribble on the whiteboard because it's a little faster than typing out code. So imagine that I have a primary template, and let's say it's of the form template type name t type name u. Could be a struct or class, I don't care. And then struct foo. And this is going to go do cool things. So an explicit specialization would lock down both t and u to concrete specific types. That's the hallmark of an explicit specialization. For a partial specialization, it's still a template. It's just more specific than the primary template here that permits arbitrary t, maybe it's a function pointer type or a reference to array or something, and arbitrary u. Like I just did with kitty, I could say, okay, I want a template, okay, and the first thing is that the names that I give to any template parameters in a partial specialization have no relationship whatsoever to the primary template. So I could continue to use t and u, and I could say, okay, template on type name, I'm just going to scribble here, t, and type name u, and this is a struct foo for I want t pointer and u pointer. And now this is a partial specialization for when I have pointers on both sides. The fact that I had said t and u here is not important. It doesn't relate to the primary template. So instead, I could have said a and b. This is exactly the same as far as C++ is concerned. So it's up to you whether you want to use the same kind of template names or template parameter names or different ones. Sometimes I will actually switch between like TU and ABC and XYZ just for clarity so I don't get confused when I'm looking at the primary template versus a specialization. So I could say, okay, I want this to be specialized for when the first parameter is a pointer and the second parameter is going to be arbitrary. And I could also say, okay, I would also like a partial specialization template on, I'm just going to continue to use different names, x, type name y. I want struct foo, again I'm saying struct here, for x and then y star. So here I'm setting up an interesting scheme. What I'm saying is my primary template is for arbitrary t and arbitrary u. If the first parameter is a pointer, I want this partial specialization. If the second parameter is a pointer, I want this one. And this works just fine until both parameters are pointers, like foo of int star, int star. In that case, you'll actually get a compiler error. I guess I can show you what that would look like. So in this case, I'm just going to get rid of the guts here. I don't need to prove that we're going to print anything. And get rid of this and all of this. Imagine I said type name t, type name u, and then I have partial specializations. Oh, I want to copy this. What? Control-C, Control-V doesn't work? Oh, I'm hitting function. It's a new keyboard. There we go. Type name A, type name B. And if I attempt to partially specialize on A star and B, perhaps I'm just trying to do something tricky that depends on the pointerness of one or more of these parameters. And suppose I say like x and y, struct kitty x, y star, and then I try to do, here I just want to instantiate kitty for, now if I said like int star and then double, this will work just fine. Okay, I don't even have to use it, and this will compile and run just fine. And there we go. Yeah, compiles and runs just fine. But if I attempted to say, so what this proves is that merely having this primary template and these partial specializations is not itself an error. It's only when I attempt to use something that has 2 pointers, for example, int star and double star, that I'm going to get an ambiguity. I could trace through all the standards, but it's actually easier to understand mentally what the compiler is going to do here. Here I'm going to get a build error, and no, I do not want to run the last successful build. And sorry, this font is kind of small. It says more than one partial specialization matches, and this is actually what we would expect, because if you look at this scheme of partial specializations, if I've got 2 pointers, then this one matches and this one matches, but in some sense neither is better than the other. They look equally good. As I explained earlier in previous parts, C++ has a complicated set of rules that tries to produce an intuitive result. And in the case of partial specializations and explicit specializations, it tries to select the most specialized match. So in this case, if I have something like int star and long, then yeah, the primary template matches, but this partial specialization matches as well. And because this matches, just sort of schematically, partial specialization matches a strict subset of the types that the arbitrary TU matches, in this case this is A star B, then if something here matches this smaller infinite set, it's still infinite, then the partial specialization is a better match. But if I've got 2 pointers on each side, both of these match. I can resolve this ambiguity, I can go back to the code here, by defining a third partial specialization. If I stop this, and I would say, let me get rid of this output window. Copy, paste. Here I can, I'll select different names, C and D. I could say this is specialized for C star and D star. And now everything will compile properly. There we go. Compiles just fine. And now I've set up a scheme of partial specializations that's completely unambiguous. If only the left side is a pointer, then this first partial specialization, A star B, will be selected. If only the second argument's a pointer, then the X, Y star one will be selected. And if they're both pointers, then even though the primary template and both of these partial specializations match, this final one is actually an even more precise match. It matches an even smaller infinite universe of types. I can show you very quickly how the standard does this. This is actually one of the cutest things, I think, about how class partial specializations are matched. There is a whole section with subsections devoted to how these are selected, and it's called partial ordering of class template specializations. And there's a whole system of rules for determining how one partial specialization or primary template is more specialized or more general than another. And it's actually defined in terms of stamping out function templates, which is clever. So if you're ever interested, you can go read how that works. So continuing on, things that may be confusing about how specializations work. Imagine I've got foo here. Okay. One thing that people are often confused by is the number of template parameters in a specialization has no effect on whether it's more specialized or less. So I've got this here. I've shown how I could say like A star, B star, but I could also say, okay, I want template on type name X, struct foo. What happens if the template parameters are identical? So this matches arbitrary x's, but they have to be identical on both sides. This is a partial specialization because the primary template will match different types, and the partial specialization insists on having exactly identical types. So it's a smaller infinite set. So there's only one template parameter here, but that doesn't mean that it's more specialized, that it's a partial specialization. I could have more template parameters. This actually freaks people out sometimes when I show them this. If I said something like template on type name A, type name B, type name C, type name D, struct foo, and suppose I've included the utility header for stood pair, I could say, okay, this is a foo for pair of AB and pair of CD. And then whatever the body of foo is. So this is a partial specialization as well. This foo insists on matching things that are pairs. But if I say foo of like int and double, then those things aren't pairs, so the primary template is selected. This is more specific because it insists on having pairs, even though it's templated on more template parameters. Here I've got 4 type names rather than only 2. So the fact that I've got more type names here does not mean that it's somehow more general. No, it's more restricted in what it'll match because it insists on matching only pairs. The other thing about both explicit and partial specializations of classes is that once this matching has been performed by the compiler to figure out, okay, which one did you want, the body of the class can be completely different. We've actually seen this going to the standard library for a bit. The classic example, although not necessarily a good example, is stood vector, which famously has an explicit specialization. It's actually a partial specialization, vector bool. If I go to the containers, sequence vector bool here, a vector, at first I said it was explicit specialization, then I remembered, oh, it's got an allocator, it's actually partial. So this partial specialization matches arbitrary vectors when the element type is bool, but the allocator type is either the default stood allocator or some user-defined allocator, and the contents of the vector bool class template are substantially different from the primary template stood vector. It's got this nested class reference that the primary template doesn't have. It's got many similar member functions, but it contains new ones like, let's see, where's a good one? Where's the flip function? Yeah, it's got a flip function that will flip all of the bits in the vector bool efficiently that the primary template does not have because vector t, that doesn't necessarily have bits that can be flipped. So when you write an explicit or partial specialization of a class, you get to determine what will be contained within that class. You can exactly follow the signatures and data members of the primary template, or you can add, remove, rename, just completely modify the guts of the class. Of course, if you say, okay, my partial specialization does not have a foobar method, and somebody tries to use your class and expects that, oh, because the primary template has foobar, then the partial specialization should have it too, they'll just get a compiler error when they attempt to instantiate that. So in general, most explicit and partial specializations will follow the structure of the primary template, but there's no hard requirement in the language. As usual, C++ lets you do whatever you want, and it's up to you to ensure that it has some sort of meaning. Typically, the standard library sort of follows this guideline, but when it comes to things like vector bool, member functions can disappear, be added, and it's completely fine. It's not like, for example, inheritance, where if you derive from a base class, then you can't say, oh, I don't want to even pretend that I don't have such a signature. Those signatures still exist on the base class, and you need to determine whether you're going to override them or whatever. Whereas templates, they're structural, and any sort of matching is enforced by the author of the class template. So here I've been following the exact same pattern. Here kitty's just an empty structure. It has a static void method. But I could easily say, okay, only this partial specialization has extra data members, or only the primary template has extra data members. That wouldn't restrict me. So I'd mentioned that you can also specialize function templates. And the way that this looks like is, let me get rid of this kitty here. imagine I've got template on type name T, void meow, and I'm going to print meow of T, it needs to be a string, like this. I'm going to call it two ways. And here I'm just going to give it an argument that I'm going to throw away. I'll just take it by value. I don't want to deal with reference at this point. And let's call meow with an int chosen at random. And then let's call meow another way with some long. Here I'll just say 0, that's long. That's just an integer suffix. So with a primary template, I would see meow t twice. But imagine I say, oh, I want to do something special for longs. Maybe I can efficiently decode them or whatever. So I can, of course, overload a function. So if I were to, and I can actually show you what that looks like, this is another thing that can be confusing because you can specialize function templates or you can overload them, and the boundary between them may seem kind of blurry at first, even though C++ recognizes very precise distinctions. So here, if I'm doing an overload, I would say, okay, here's a meow overload that's for longs. And here I could say meow long. Now I'll write the signature differently. Meow t. And this is just an ordinary function I'm overloading here. It's not a template at all. Not a specialization. If a book tells you this is a specialization, it's wrong. And this will compile if my brain agrees with C1XX, and yes. So when I call meow with an int, let me move this down, then both of these are actually viable, as we saw in overload resolution, but the template's an exact match. The int doesn't have to be converted to long. In the case when I call it with a long, again, they're both exact matches, but a tiebreaker comes in and says, oh, they're equally good matches. The non-template, I'm going to choose that one as a tiebreaker, so that's why I get meow long called here. There's another way to do this that does not involve overloading meow at all, and that's to write an explicit specialization. So here I could say, okay, template, and again, an explicit specialization is introduced by empty angle brackets, looks like a diamond, and here I would say void meow long, and then here and here I could print meow long. It's an explicit specialization. Or full, if you prefer that terminology. And this will have the same effect, except with different syntax, and something different is going on behind the scenes. So if I terminate and recompile, here we go. Again, meow int selects the primary template, and meow 0L, now this selects the explicit specialization. So conceptually what's going on here is I only have one function template sitting around, and its signature is meow taking t. What will happen is name lookup, template argument deduction will deduce t to be either int or long in this case, and then overload resolution says, oh, there's only one overload. You win by default. And there's no question of, oh, does this other thing compete? There's only one overload available here, and then access control that's not a member or anything. But after all of that happens, then the compiler will say, oh, you selected a function template. Has it been specialized? Because yeah, I see this primary template here. I'll call that if I don't see anything better. But this specialization in some sense replaces the primary template. Once this has been specialized, there's no way for me to go and say, okay, I see you've got meow long there, but I would really like the primary template even though there's been an explicit specialization. That's not possible. The explicit specialization completely replaces the content of the primary template. If I wanted to sometimes access the primary template, I'd need to write my code differently. So there's no overloading that happens here, and sometimes this can be quite desirable. But then this is where things get a little confusing. In C++ 98, 03, and C++ 11, there is no such thing as partial specializations of function templates. You can partially specialize a class template, as we saw, where you've got a primary template for arbitrary t and then a specialized one that is only for like x star. But if I attempt to do this with a function template, then I don't get partial specialization. The way that I suggest people remember it as is anything that looks like a partial specialization of a function template is actually an overload. And this is almost as good, like 99% of the time. It actually produces a desirable effect. But there are some times when it's not quite what you want. So I can show you an example of this. This is getting into sort of advanced territory. I found like one use for this. Imagine I've got a primary template, and I'm like, okay, I would like to provide a meow that only works for pointers. So we could use tag dispatch to check if t is a pointer and then call a helper function. But if I'm trying to do it at a single step, I could say, okay, template on type name x, void meow for x star. Okay, this is not a partial specialization as it would be for like a class template. This is an overload. I've got two different templates, in this case they're primary templates, one for arbitrary t and another one for x star. And if I attempt to call this, for example here, I'll just keep these two calls, and then I'd say meow, and let's get a pointer here, I'll static cast, because I need a type, and let's say double star from null putter. Because null putter itself is not a pointer type. It is just convertible to any pointer type. If I compile and run the guts of this are completely wrong. Meow x star is an overload. That's correct. If I compile and run this, then as I would expect by writing this, if I call it with a double star, then I get this meow x star. But I have not partially specialized this template for t because there's no such thing. Instead, I've got a completely separate overload. Now, it had the desired effect that this one gets invoked for pointers and this one gets invoked for other things, but it's not going through that usual mechanism. It's going through overload resolution, which we saw back in part 3. So this usually works. This is usually desirable most of the time. But what if overload resolution is not applicable? This can happen if you have no arguments. So imagine I've got meow, and like I said, advanced territory. And imagine I try to write, and this is bogus code, something like meow x star here, and put something in here. If I try to compile this, this should freak out. Yeah, because it's for arbitrary x. I'm trying to compile it in my brain before I run it through C1XX. And we get compiler errors. Excellent. And it says, I will read this out because it's small. It says, void meow, function template has already been defined. See declaration of meow. It's getting confused. And that's because I cannot partially specialize a function template. And this is not an overload either. I can't overload a function that has 0 arguments because overload resolution only looks at arguments. It doesn't consider return types. It doesn't consider anything else. So even if I were to, of course, these calls are no longer valid. Even if I were to provide explicit template arguments like meow int and meow long and double star, this doesn't help either. The call site has no effect here, and here I could just say null putter, because the definition is not correct. If I try to save and compile, the compiler still rejects it, saying function template has already been defined. So what if I've got this situation where I want to do something equivalent to partially specializing a function template, and yet I don't have arguments available that'll do overload resolution, or for some reason overload resolution can't distinguish between them? What do I do? Well, one thing you can do is you can just write a single primary template and then internally use something like tag dispatch to discriminate on t and say, okay, if t is arbitrary, then go call this one helper. If t is x star, perhaps by using type traits, then go call this other helper. We've seen in previous parts, or I believe in the STL series, how to write things like that. But what if you want to do it without using chains of helpers like that? One workaround is to use helpers, but to use static member functions of a class template. In this case, I can just sketch it out, what it would look like. Imagine that I've got template on type name t. Here it can be struct. Helper. This helper is a primary template. And I could say static void do thingy. Do is a keyword. And taking, here I could put anything I want, because it could take actually nothing. And then go do something based on T. Maybe it's going to construct T or print out the type name of T or whatever. And no semicolon there. And then I can partially specialize a class template, because that's totally legitimate. Template on type name X, struct helper, for only X stars, not anything else. And then here, I could have totally different guts, but in order to do this trick, I want the exact same signature. So I'll say static void do thingy, no arguments, and then go do something only for pointers. And then if I just call this with the syntax helper, and I need to tell it, okay, which class template do I want, because there's no such thing as template argument deduction for class templates. So here I would say, okay, I've got, double star, and then invoke a static member function do thingy with no arguments. Then this completely bypasses the fact that I can't partially specialize a function template and that I can't use template argument deduction when there's no arguments. It says, okay, I've got a primary template helper, and hey, I'd like the helper for double star. The compiler will say, oh, I see a partial specialization that's even better. I'm going to give you that one. And then go invoke do thingy on that. So you will get this one, and that almost always has the desired effect. I have not encountered a case where even that level of helper is unacceptable for some reason. It's occasionally been considered whether to add partial specializations of function templates to C++. I know at one point I believe was proposed for C++ 11, but apparently the committee was busy and had more important things to tackle. So we may see it at some point in a future version of the standard, but for now, if you ever want anything that resembles partial specialization of a function template and you can't simply use overload resolution, then for the time being you'll need to use something like this struct static member function workaround, or things like tag dispatch with nested helpers. So let's see, I was going to show, okay, and one other thing about this syntax that confuses people, actually I guess I can show you the code, is that this C++ kind of has an aversion to adding new keywords for things. You could imagine a language where you would have to say, like, explicit specialization template, blah, blah, blah. But instead, C++ minimizes the number of keywords and relies on syntax like empty angle brackets to say, okay, this is an explicit specialization. One of the confusing things is that two very similar things use almost identical syntax. So if I've got template type name T, struct meow, then if I say template, I'll just spell out everything out in full here, empty angle brackets, struct meow, for int. This is an explicit specialization for int that will be used whenever you request meow int. Instead, if I write template, and this syntax is somewhat rare, struct meow, and I'll put a different type here, long, whatever type, semicolon. This is not an explicit specialization. Explicit specializations are always introduced by empty diamonds. Instead, if you ever see template immediately followed by either a name of a struct or a function, that's an explicit instantiation. Totally different, and yet it has extremely similar terminology, explicit something-somethingization. And they're actually right next to each other in the standard. So the way that templates ordinarily work, both class templates and function templates, is that they're instantiated on demand. Remember that a template is a cookie cutter. It stamps out a potentially infinite family of cookies made out of different types of dough, but of the same form. Every vector kind of resembles one another because they have the same kind of methods, even though they generate potentially radically different object code. So when you request, okay, I want to use a vector int, or I want to use a pair of long and const char star, and go use so-and-so member functions, the compiler needs to generate both a class definition and then any implementations of member functions that you invoke. It needs to stamp those out and put them in the executable. So the usual way that C++ does this is with implicit instantiation. Basically, as soon as you try to use something, then it'll be generated in the binary, and the linker will do this thing of smashing everything together. That's why you can have one translation unit, which is a source file plus all of its included headers, use a vector int pushback, and another translation unit also use a vector int pushback, and the linker will have two different instantiations generated code of vector int pushback, and yet the linker will say, oh, those are both member functions of a class template. I'm just going to hope that they're identical, and if they aren't, things will explode horribly, but if they are, everything will link awesome and run perfectly fine. So implicit instantiation is what we all depend on, but sometimes in rare cases you want to say, okay, I really would like to stamp out this function template for so-and-so arguments, even though I'm not necessarily calling it in this function, in this translation unit, or I want to stamp out this class template and all of its member functions. And that's the explicit instantiation syntax. I could explain more about that, but because it's relatively rare, I just want to make sure you're aware that this sort of syntax exists. C++11 adds something called extern templates, which is even more advanced. VC has actually supported that since, I believe, like VC 2.0, although in VC 11, Visual Studio 2012, it received a few enhancements to make its behavior conform to C++11. It's very rare that you ever need that. I really have never used that in my own code, but in certain cases, messing around with explicit instantiations and extern templates can be useful. So back to specializations. There's this cute thing that was hidden in the standard. There's a limerick in the standard. Let me show it to you. It is down here. Yes, in N3376. It is paragraph 7. And it's this final sentence here. And it's actually a warning. It's preceded by this hilariously complicated paragraph. And the warning says, when writing a specialization, be careful about its location, or to make it compile will be such a trial as to kindle its self-immolation. It's warning that you're going to set yourself on fire if you don't pay attention to this paragraph. The paragraph is horrible. What it means that is, if you're ever working with either explicit specializations or partial specializations of class templates or function templates, you need to be very careful about where you declare them. And there's a whole bunch of things you can do, and I would have to look at the standard to figure out whether they're supposed to work or not. But the iron rule is to declare everything before you could ever possibly instantiate stuff. And the standard actually has a good example. So rather than scribbling stuff out, I can magnify this example and show you what it looks like. So here, they've got a class template array, and they've got a function sort for array of t. These are primary templates. And then they've got just a plain old function f, doesn't matter what it's doing. It's going to invoke sort on an array of string. So this will use the primary template. Everything here is cool so far. But then imagine that the user says, oh, I want to do something special if I'm sorting an array of strings. I've got an efficient implementation that can compare characters and then do something efficient. So I want to have an explicit specialization for sort array of string. So I'm just going to go define that. I'm going to define it down here. So if this explicit specialization is defined and declared after the primary template is used, this is an error. This violates that limerick rule in the standard. You've specialized something after you've tried to use the primary template. And this is extremely bad because imagine what the compiler could do. The compiler could stamp out an implementation of the primary template for sort array of t, and then in another translation unit, it could actually instantiate this specialization. Then when the linker tries to fold these together, it may pick one of them randomly. And you would get maybe the primary template's implementation used when, oh, you declared a specialization, or vice versa. That would be extremely confusing. However, it's okay to specialize something as long as it has not yet been instantiated. So here we've got the example, okay, I'm going to have an explicit specialization for sort of array of char star. And because in this translation unit, sort for array of char star has not yet been instantiated, this is legitimate. So this is showing you, with this error, an example of bad code. Now, if I were paranoid, and I'm always paranoid, the way I would avoid situations like this is imagine I've got template on type name T, okay, and then blah, 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 void sort for like array of T. Okay, so in the most general case, imagine I've got a system of overloads, whether overloaded functions, or maybe I've got class templates that are using each other, and the function templates are going to call each other, or the class templates will instantiate each other. If I want to be ultra paranoid, what I'm going to do is I'm going to declare the primary template, declare any specializations, whether explicit or partial, and then go actually define everything in a separate step. So here, this is the way to absolutely avoid any badness. In a header file, so this would be sort.h or whatever, I would declare the primary template and not define it yet, because if that definition uses other stuff, that could try to instantiate a specialization that has not yet been declared. Then I would go say, okay, I want an explicit specialization, so template, empty diamond, sort of, in this array case, it's unlikely that they would try to use each other, but in other cases doing tricky template things, it is quite possible to say, oh, I'm going to handle a base case, and then I'm going to go define a reduction step and blah, blah, blah. Array of like string, ref, declaration, and then go declare anything else, maybe other explicit specializations, or if I'm doing classes, primary class template, and then partial specializations of a class. So declare, 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 and then once all the declarations have been seen by the compiler, then it is safe, and it follows this limerick rule to then go define things in any order because the declarations have been seen. So I could then define by saying template on type name T, void sort for array of T, ref, and then go do cool things, close brace, and then go define the explicit specialization template on empty angle brackets, sort for array of string ref, and then actually define it. One thing that is useful to understand here, and this is a general rule not related to templates, every definition in C++ is also a declaration. A declaration says, hey, I've got this thing. Whether it's a class, like here's the name of the class, or hey, this is a class and it's a template, or a signature of a function, like hey, I've got this function here. A definition actually provides either what the function does, or it provides the layout of the class, including its data members and any member function signatures. It's like the actual guts of the thing. If you go define either a class or a function or a class template or a function template, that also declares it. It's saying, hey, I've got this thing, and by the way, here it is. So that's why if I simply had this stuff, I'm defining sort array tref and also declaring it, and then I define array of string ref and also declaring it. If these depend on each other in any way, that would be an attempt to use this, potentially, this explicit specialization before it had been even mentioned. Because in most cases, you can think of C++ as being parsed top-down. That's not always true. There is an exception to that in classes, but in general, you should think of it that way. Whereas if I separate the declarations and the definitions, I say, okay, I've got a primary template, hold on, I'm not going to show you the body yet, and then I've got an explicit specialization for string ref, array of string ref. I'm going to do something special here. I haven't told you what it is yet, but just be aware. And then go define everything. This strictly follows the rules of the standards, and you will never get into trouble if you just declare everything before you use it. And the worst part is if you violate that rule, it's essentially a one definition rule violation. You'll get undefined behavior in general, and what will happen is everything will compile, everything will link, and the program will crash horribly or misbehave, or worst of all, do exactly what you expect until 5 years down the road it breaks, and then your successors have to go figure out what went wrong, or in the worst case, you have to go figure out what went wrong 5 years ago and you don't know what you were doing. So when you ever see rules like that aren't guaranteed to be diagnosed, you need to be really, really careful to follow them. Anytime anybody mentions one definition or rule, that's a rule to follow. And this limerick here about self-immolation is also a very important rule to follow. So that's all I want to talk about for specializations. In part 6, I'll be covering the new features that are being added to Visual C++. I can't tell you what they are yet, but we'll see that pretty soon. So see you then.